All right, I guess I'm live now. Uh, Let me send invitation to Jason. And guys, how are you? I'm waiting for Jason to accept the request. Sorry. So I hope everything is going fine with you guys. Um, I'm spending my time during Corona taking some online lectures and all those things, and I hope you guys are doing the same. Okay, I guess Jason is here. Jason, if you haven't received my live request, you can send me here. Oh, Akshay, thank you very much. I know you're kidding, but still, thanks a lot. Hey, Shipra, what's up? Thanks a lot. Wait, let me send it again. Yeah, I'm waiting for Jason. He might be having some connecting issues, and that's why it's getting delayed. Still, let's have some normal conversation. So, what's up with you guys? Oh, Vivek is also here. Hi, Vivek, how are you? Yeah, I'm absolutely fine. You say? Okay, first, send your request, view, go live. Okay, and I guess we are good to go. Waiting for him to accept.
Hey,
All right. Hey, Jason, what's up?
not much, not much. How are you?
I'm absolutely fine. You say what's going on?
Um, well, not a whole ton. Just been doing research and that kind of stuff. I mean, it's the morning, so it's just gotten started. But yeah,
Okay, that's cool.
just
Yeah. First of all, thank you very much for, taking out some time from your busy schedule. And I
yeah, of
was
course.
really looking forward for this conversation.
Yeah, me too.
Yeah. So, Jason, before starting, can you introduce yourself to our audience so that they can know you better?
Yeah, okay. So I'm a fourth year PhD candidate at University of California, Irvine. I study particle theory, and specifically, I study particle theories of dark matter. So whether that's the kind of standard canonical WIMP story, if it's something more to do with maybe it's WIMP-like, but it has some more complicated cosmology, or maybe it's something completely different. I'm kind of studying just kind of different theories of dark matter, what dark matter could be, and what the experimental constraints, what do experiments today say about what dark matter could and couldn't be.
Yeah, that's great. And the thing is that I actually want to go in this field only, and you are like a guardian kind of person for me. I can constantly ask things to you, and that's why I thought that you should be the best person to have an interaction about the matter and the standard model about all those things.
Oh, thank you.
So, talking about the properties of the matter, let's start. What actually is matter? How can we, define all the matter we know in a nutshell? Can you describe it?
That is, I mean, that's a difficult question. At the most fundamental level that we understand, everything is made out of these quantum fields that permeate the entire universe. And these
Okay.
fields, very, very similar to like an electromagnetic field or something like that, they exist throughout the universe. And what what particles are and what matter is are these fluctuations, or they're these excitations in the field. So you get this field that has some value everywhere in the universe, and then you get these spikes. And those spikes in the field are where you get particles. Um, the most fundamental language, though, when you talk about these kinds of things, is in terms of the quantum fields, um, and all the mathematics. That's the most precise way to say it. And then you can get when you get those spikes, you can actually get different types of behavior. They can clump together, they can interact with each other, different types of fields through their different types of interactions and all that kind of stuff. And then you can get more complicated things like, the most fundamental building blocks we know of in terms of the matter particles are things like quarks and electrons, or to be more precise, quarks and leptons. But quarks and
Um,
electrons, sorry, go ahead.
yeah, yeah, please continue. I will ask later.
Okay. Those can combine into more complicated things, right? You can get quarks that interact through the strong force to combine and make some like baryons and mesons, which are either a quark and an antiquark or three quarks. Um, and you can also get baryons and electrons to bind together to make atoms, and all that kind of stuff. Um,
Uh,
and so you can
that's
get,
cool. And I think quantum field theory will also explain that how some particle, uh, disappear from one place and then suddenly appear at another place, and how does this thing happen during, in quantum field. So I guess we can explain this using quantum field theory.
yeah, so if I understand you correctly, basically, uh, you can understand this by thinking about, well, since it's all these particles are made from the same quantum field, uh, if they say, if you have two particles or something like that that annihilate at a particular point, right, you could imagine that you would get um, that some other source of energy or something like that could spontaneously create two particles of the same thing, of the same type. Maybe it's electron-positron pairs or something like that. But even if you kind of annihilate these particles out of existence, you're not really, uh, violating any sort of matter conservation laws in this kind of quantum field theory context.
Cool. So your field of specialization is dark matter. But before coming to the dark matter, I want to discuss some aspect of current standard model, and especially regarding the weak nuclear forces, which I find to be very interesting and which explain the interaction of the neutrinos and particles like that. So
Mm-hmm.
can you explain that how can we distinguish weak nuclear forces from other forces?
So one thing that's very interesting about the weak nuclear force is that it's a chiral field theory, which means that um, it interacts with particles in a different way depending on what is called their chirality is. So there's two chiralities. You can talk about left-handed particles, and you can talk about right-handed particles. So with an electron, you can have a left-handed electron and a right-handed electron. It turns out that the weak nuclear force only interacts with left chiral things. So it will not interact at all with a right-handed electron, but it will interact with a left-handed electron. And so
And when we
the
talk about these sterile neutrinos, I guess they comes in the form that do not interact with weak nuclear forces because of their chirality.
exactly. So we've only seen left-handed um, neutrinos, and the reason why that is because left-handed neutrinos, interact with the weak nuclear force, but they're completely electrically neutral, so they don't interact via the electromagnetic force, and that makes them incredibly difficult to detect. But if you already take away, then with a right-handed neutrino, you take away their weak interactions as well. What are you left with?
Mm.
Well, there could in principle be, um, some very, very weak force, whatever you call it, some beyond the standard model thing, or maybe it's just gravity or something like that, in which case it's going to be incredibly difficult to detect. Um, so there's a reason why we haven't seen right-handed neutrinos, and it's not particularly surprising based on our understanding. Um, and it could take definitely some time to truly detect a right-handed neutrino or something like that. Um, but we expect it should be there. And it could have been that there were no right-handed neutrinos if neutrinos didn't have any mass. Okay, so if
Mhm.
they didn't have any mass, then it could have been that every single neutrino that was ever created would have been left-handed, and that would have been completely consistent. Um, the issue with that is
Mhm.
that in some experiments, um, at places like, there's some places in the U.S. I think it's Dune. Is that right? I actually don't remember some of the experiments. There's some neutrino oscillation experiments
Yeah,
where
I remember that experiment.
okay, yeah. So there are experiments where they've detected neutrinos oscillating from different, between different types of neutrinos. So there's electron neutrinos, there's muon neutrinos, and there's tau neutrinos.
Mhm.
And the most consistent picture that we have is that if you start off with an electron neutrino, regardless of any of the interactions that you have, right, spontaneously, an electron neutrino can turn into a tau neutrino, and then can turn into a muon neutrino, and so on. Okay?
Mhm.
And that experiment um, tells us that neutrinos have a small but non-zero mass, which kind of requires us to not just have left-handed neutrinos in the universe.
Mhm.
So that's one thing that distinguishes the weak force uh, from the other forces. And there's also just interaction strengths, right? Uh, to distinguish from, say, the electromagnetic force, um,
Mhm.
other than just the chirality issue, um,
Okay.
the interaction strength is different. They are related. In fact, there's the electroweak force that you can combine them at early times, but they are different values when you come to present day. And then also, one thing that makes the weak force so weak is the interaction strength actually isn't that small. The constant, the coupling constant that determines the interaction strength isn't that small. What makes it
Mhm.
really small is the fact that the particles that mediate the weak force, the W and Z bosons, that they're
Mhm.
massive. They're actually quite heavy in terms of, like, if you're thinking about neutrinos or electrons or something like that, right? Um, they're about 100 times or 80 to 90 times the mass of the proton. And that fact that the mediating particles are massive makes it much, much weaker. It actually exponentially decreases the interaction strength. Um, and so, that's what makes the electromagnetic force, right? That's a long range force, purely due to the
Mhm.
fact that the photon is massless. So it allows it to travel over far distances. But the larger the mediator's mass would be, the shorter length, the shorter distance of a force that it is, and then it makes it, kind of effectively weaker.
Mhm.
And so since the mediator for the weak force is very heavy, the weak force is quite weak.
Right. Now, coming back to the weak nuclear forces, so I have two Feynman diagrams with me here.
Okay.
I hope you can see here. One is, with the photon and other with the Z boson, but the interaction seems to be very similar. In normal case, how can we distinguish these two interaction as shown in this Feynman diagram? I hope you can see it properly.
Um, yeah, so there's a lot of details that go into the Feynman diagram, so you can draw them and all that kind of stuff, and it's great. But for if you're wanting to do a calculation with them, there are associated Feynman rules that you have to write down and all that kind of stuff for each part of the Feynman diagram. So what would actually happen for the photon versus the Z boson is going to be there's going to be slightly different Feynman rules that,
Mhm.
even though they're basically the same type of particle, the photon and the Z boson are both vector bosons. Um, they have slightly different interaction strength, and they also have, well, they have different masses as well, and they have the whole chirality issue. So the point at which the fermions, I think those are electrons, I couldn't quite read it, but the two fermions meet, and you see the either the photon or the Z boson, that vertex, the point at which those three lines meet, um, there's a particular rule that tells you, some multiplicative factor to put in there, and that would be different. Um, in principle, right, um, you'd have to write down, yeah, let's see, you'd have to write down specific chiralities of the electrons and that kind of stuff to truly write this Feynman diagram correctly. And yeah, I think that's the the way that I want to say it. Um, yeah,
And like,
ultimately,
I've thought that if we want to differentiate W boson and Z boson, fundamentally, how can we do that? Like, I'm aware that with the help of W boson, we can explain the decay of one particle into the another. But like, what's the how they play the role in weak nuclear forces? When does the W boson play the role, and when does Z boson play the role?
yeah. So, um, really, they're one and the same thing. Okay, so that's not quite a completely true statement, but they do come from the same field. Okay. Um,
Okay.
Truly fundamentally, the photon is actually mixed in there as well. But the only true difference is that the W and Z bosons just change are different by electric charge, right? So you have a W plus and a W minus, and then you also have a Z, and the Z is neutral electrically.
Mhm.
And so it really just depends on it depends on what your interaction, is going to uh, have. If you have excess charge, right, that you're mediating away, then it would be uh, mediated by the W's. If it was something that was a neutral thing, right? Let's say that you were decaying, something was uh, decaying and emitting two neutrinos. Well, uh, you can't make two neutrinos from a W plus or a W minus because neutrinos are electrically neutral. So it would have to be mediated by a Z decay, something like that. So it just kind of depends on the process and depends on those kinds of circumstances.
That's cool. And like that was a very detailed information. Thanks for that. And now coming to the dark matter thing, now we know that dark matter is dark because it do not interact with electromagnetic force, which is the force responsible for our, vision and sight and all those things. So
Hmm.
dark matter is kind of force which do not interact with it. But can you explain in detail what actually is dark matter if you are talking from WIMP perspective, from weakly interactive massive particle perspective?
Yeah, so there's been a long history of kind of dark matter theories called WIMPs, which is a weakly interacting massive particle. And so the weakly interacting canonically kind of refers to the weak force. So it interacts via the weak force. It doesn't have to mean that. So you can mean something like, oh, it's just generically a weak interaction. Uh, I guess lowercase w weak. Um, but I'm going to be talking about just kind of the standard canonical interacts via the weak nuclear force. Um, and so what this is just a dark matter with a some mass. Okay, it's going to be on the order of 100 times the mass of the proton or so, um, somewhere around there. And it's going to interact via the weak nuclear force. And the reason why this is nice is because if it interacts via the weak nuclear force, it doesn't necessarily need to interact through light or through the electromagnetic force. And that's actually very similar to neutrinos, right? We know that neutrinos have exactly the properties that I said, aside from the mass is just much lighter. Um,
Hmm.
and so that might be a good place to start because we know of a particle that is electrically neutral that interacts via the weak force. That's a great place to start. What
That's
also
cool.
turn what also turns out to be very nice is that
Hmm.
uh, these kinds of particles just pop out of lots of beyond the standard model theories. So
Okay.
to name one very famous one is supersymmetry. So
Hmm.
supersymmetry uh, basically proposes that you have, you know, a partner particle to each of the standard model particles that we know of. There's an additional particle of the different particle type. So there's bosons and fermions at the most fundamental level. Um, if there's a boson in the standard model, it has a fermion superpartner. If it's a fermion in the standard model, it has a boson superpartner. So you're basically doubling the number of particles in the standard model. But what it does
Hmm.
is it just predicts these WIMPs. Um, the kind of most standard thing is called a neutralino. Okay,
Hmm.
neutralino dark matter. Um, and these have the exact properties of being WIMPs, while also supersymmetry not being, uh, you know, the idea of supersymmetry was not to predict dark matter, right? There was no dark matter in mind when that first came out. It was really trying to solve the problem of what was going on with
Mhm.
the Higgs mass. Um, but you get these theories that predict that you should see these WIMPs, that they should exist. So it's some nice confirmation if you're getting a theory that solves some other problem of the standard model and then gives you dark matter for free. The next thing that's
Correct.
very, very nice about WIMPs is that there's something called the WIMP miracle.
Hmm.
And the idea is, and this is a very standard story for people to tell, but it's not, known to be true. I just want to make that clear. It's kind of the most conservative thing that you could think of doing. But if you take a standard WIMP and you kind of take the standard model plus that WIMP dark matter and extrapolate back into the early universe, what happens is those WIMPs are thermally produced just by the temperature bath in the early universe. And
Okay.
as the universe, these particles can also meet and annihilate, creating other particles. But in the very early universe, they're in thermal equilibrium. So you just have, some rough amount of dark matter in the early universe. As the universe expands, it cools. And as these annihilations are happening, you can start to become out of equilibrium, which means that maybe you're annihilating more dark matter than you're annihilating standard model stuff into dark matter. So you're depleting the amount of dark matter as the universe basically cools and expands.
Okay. And
Eventually,
it's all
though,
equilibrium. Cool.
oh, sorry, go ahead. What did you say?
Yeah, I was saying that it's going towards the equilibrium. Like,
Yeah,
so does it mean that dark matter particle can decay into standard model particle?
generally not decaying. So generally, we want there to be dark matter today, and for it to be stable on cosmological timescales. So you want to forbid any decays to happen. But what you can have is two dark matter particles meeting and annihilating into standard model stuff. That is perfectly allowed. And the reason why that is because as the universe is expanding, we initially had a lot of these annihilations, which was depleting the dark matter abundance, right? The amount of dark matter that was in the other universe. Um, what happens though is that as the universe is expanding more and more and more, the dark matter starts to get further and further apart, and it starts to get to be harder for the dark matter to meet and annihilate with each other. Okay, so the dark matter now is so far apart that it gets more difficult to find each other, and eventually it just completely stops happening, or at least it stops happening incredibly efficiently, and it basically locks the abundance, right? The amount of dark matter that's actually in the universe. It kind of locks that amount in, and that's called the relic abundance of dark matter. And it turns
Hmm.
out that if you and that's perfectly fine right now you might look for dark matter annihilation today, but it's nowhere near as efficient as it was in the early universe, and it doesn't happen that often because things are far apart and all that kind of stuff. Um,
Is there any
but
possibility that we can detect those particles which were created during the early universe today on Earth using any of our detector or observatory or any detection method?
yeah. So there are three detection methods, and I'll get to that in just a moment. The the one thing that I want to say before that is that the thing that's very nice about WIMPs and that's been very attractive for a lot of people is that these WIMP models, if you do this story and you take a standard WIMP with electroweak strength interactions, all that kind of stuff, you get the right relic abundance. You get the right amount of dark matter that we see from measurements today using things like our telescopes and you know, from the CMB measuring through gravitational lensing from galaxy rotation curves, all that kind of stuff. To figure out what the amount of dark matter is today, we can do that. And taking a standard WIMP and doing that early universe calculation gives you the right abundance and matches with current day observations. So that's the thing that people were like, okay, this is the WIMP miracle. It miraculously, in addition to all these other things, we know that particles that only interact weak force exist. Um, we know that other theories that aren't just dark matter theories predict these WIMPs, like supersymmetry, for instance.
Mm.
And then it also satisfies the correct abundance of dark matter today. So it seems like, okay, that's it. That's so compelling. And it has been very compelling. People have studied this for 30 or so years, maybe a little more. Um, and we haven't found anything yet, but it's still possible that they could exist. It's just difficult to measure these things. And so that brings me to your question about the experiments. So there are some different types of experiments that you could imagine, and that exist. So there's what are called direct detection experiments, there's indirect detection experiments, and then there's collider experiments. Okay, so I'll start off with, I think, colliders, because they're the most kind of familiar to people in general. But what happens is, say at the LHC, you have protons colliding at super high energies, and at those super high energies, you can convert that energy from the collisions into higher mass particles. Maybe they only exist for a little while, but you can still create them, and then they can decay and all that kind of stuff. That's like how they discovered the Higgs at the LHC. And so what you could imagine doing is that if dark matter does interact with the standard model, which we hope it does, because that would make it, that would mean that we could detect it through other ways than just gravity. And if it's just gravity, then it'd be nearly impossible on the microscopic scale. But if it does interact with the standard model, then you could imagine creating it at the LHC, because, right, you get enough of these, you get enough of this energy, and because it interacts with those particles, you can spontaneously make, maybe do pair produce, right? Right, you can get this energy to spontaneously have a dark matter and anti-dark matter pair.
Okay.
And so that's one thing. That the thing is, though, is that you will never you'll never detect the dark matter directly from that experiment. What you'll see is that the dark matter, if it's created, will just kind of fly out of the detector, not getting detected. But if you look at the amount of energy that was before the collision and the amount of energy that was after the collision, if the dark matter particles are just leaving the detector, then you have some missing energy. So that's one of
Okay.
the signals.
Before you go any further, I have a question. Like
Sure.
you said that it might create dark matter and anti-dark matter. The way we understand matter and antimatter by using chirality, I guess that's the best way to understand the matter-antimatter difference. So when we are talking about dark matter, can we apply the same rule to it, or is there any different mechanism to differentiate dark matter and anti-dark matter?
So I mean, it kind of depends, because we don't truly know whether or not, know what type of particle dark matter is. It could be that dark matter is its own antiparticle. It could be that they are two distinct things. And so there's a lot of different ideas. You could talk about, maybe they have different
Majorana,
chirality.
right, right. Okay.
Yeah, absolutely. So we really don't know at this point, and it's uncertain. You could even have, you could even have that dark matter isn't even Dirac or Majorana. Maybe it's not even a fermion at all, right? Maybe it's a scalar, maybe it's a vector.
Right.
And in that case, you could imagine that it could just be, without any additional constraints, that it's just its own antiparticle.
Cool.
So yeah, it's difficult to say at this point, but there's a lot of different, things that you could play around with. There's a lot of wiggle room with dark matter models that you can play around with, because, there are things that we know that 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 really don't work from the experiments that I'm going to describe in just a second. But there is still a lot of things that could work, and a lot of things that people haven't explored yet. So there's a large range of things that we can do. Okay, yeah. So the next experiment that you could that we're doing, or not me personally, but physicists are doing, is direct detection experiments. Okay, so direct detection experiment is kind of as the name suggests, the most direct way that you could measure dark matter or detect it. And what you have is basically just a detector that has some atoms in it. Okay,
Okay.
and those atoms uh, can basically, if you isolate them as well as possible to things like cosmic rays, other background noise, and all that kind of stuff, you could imagine a dark matter particle like a WIMP coming by, passing through the Earth, and eventually bumping into one of the nuclei of those atoms that's in the detector. And when it does that, it kind of jostles the atom a little bit, and you can see an actual signal from there. Again, that's sounds like a very straightforward thing to do until you think about the types of background that you need to subtract and all this like systematic stuff that you need to do, and then it sounds incredibly difficult. But they've managed to actually do this. They haven't measured dark matter yet, but they've gotten incredibly good sensitivities so far. There's experiments
I
like
think
the Xenon 110.
using this method or xenon detector. I think they are working on that principle only.
Um, Sorry, you cut off for a little bit, or it was a little bit warbly. What'd you say?
I was asking that we have a xenon detector to detect dark matter and such kind of particles. So I think they falls into that category only.
Yes, yes. So the Xenon 1 ton detector, yeah, is a direct detection experiment, and yeah, it basically just waits for dark matter to bump into the xenon atoms, um, because it should be able to pass through. You know, it's pretty deep underground. The dark matter should just be able to pass through the Earth's crust and then make it to the detector. And every once in a while, depending on how weakly the dark matter interacts, you would expect different amounts of, or the different rates at which the um, dark matter will interact with the xenon. And effectively, what they can do is, well, since we haven't detected dark matter, they can tell you, okay, well, if dark matter had this coupling strength or this interaction strength and this mass, then we should have seen it. But we
Okay.
didn't, so we know that we can exclude those masses from being the potential dark matter candidates. So if your theory predicts that it should have this interaction strength and this mass, then it's ruled out, and then you should move on to something else, or you should adjust the theory maybe to have it be something else. Um,
And
but
I
it
guess
does,
if we want to go for the extra mass range, then we have to improve our detector to next generation detector.
yeah. So you can make things like bigger detectors. You can maybe increase the sensitivity by increasing your systematics and measurement methods and all that kind of stuff. I am not an expert in that because I really only do theory, but there's a lot of things that people are doing, and there's actually a next generation um, experiment to Xenon 1 ton called LZ, um, and LZ does improve the bounds by quite a bit, and it could help to either detect or rule out a pretty large class of dark matter theories.
Cool. So these are the detection methods. Now, before going to my next question, I was reading your paper regarding the emergent solution to strong CP problem, and
Mm-hmm.
like I was going through it, and I found it very interesting. So, can you explain our audience more briefly about it, like what it is related to and what kind of thing it is answering regarding dark matter?
Yeah, um, so I'll have to start off with the kind of traditional Axion story and what's going on there, and then I'll talk about the paper. Um, so the idea that we're playing with is, this problem called the strong CP problem, and what this is that uh, it's really having to do with the strong nuclear force, hence the strong, and the CP problem um, is talking about CP violation. And just for
Okay.
the sake of being brief, what this has to do with is that uh, if you have CP violation in the strong sector, this means that the neutron should have an electric dipole moment. Okay,
Okay.
so that is something that you can look for. That's an observable. And experiments have looked for the neutron electric dipole moment. Um, but the thing is that they haven't, when they've tried to detect the neutron electric dipole moment or they've measured it, it's very small. Actually, they haven't found any signature of electric dipole moment, but what the only thing they can do is they can't say it's zero, but they can say it's smaller than a certain number. But it's completely consistent with zero. It's like 10 to the minus 10 or something like that. Sorry,
Okay.
it's 10 to the minus 26 or
Wow.
lower.
That's
Um, the particular parameter that controls that value is called the theta parameter in QCD, quantum chromodynamics. And that theta parameter we would expect from theory to be of order 1, so around the value of 1. But if you kind of do the calculation, these neutron electric dipole moment experiments predict that it should be 10 to the minus 10 or smaller. So that's a 10 order of magnitude difference from theory and experiment from what we'd predict, at least. Maybe it's completely zero. And so the thing is, okay, what's going on here, right? Maybe it's possible that that theta parameter, our expectation of it being of order 1 is just a naive expectation, and it could just be that the universe gave us a very small theta value. You know, that is perfectly fine. That's not a particularly satisfying answer, though, because you can't really do anything with that. You just kind of throw your hands up and say, okay, that's it. The normal solution to this problem is that that you can introduce a new particle that interacts with that interacts with gluons in a particular way that makes it so that if you include the normal contribution of the theta term in QCD and you include the extra particles contribution, that they cancel each other out. And so you get this effective theta, an effective theta that it's basically goes to 0. Okay, and then what that does is that basically makes it so that the neutron electric dipole moment goes to 0 while still having that order 1 theta, the original theta term, but it's just getting canceled by this extra field. And that field is called the axion field, okay? It turns out that the axion also, well, this is a QCD axion. There's a more general class of axion-like particles that people, tend to call axions. But it solves this strong CP problem by saying that, okay, we expect CP violation and a neutron electric dipole moment, but this extra field, this axion field is there and makes it so that actually doesn't exist. Okay, the CP violation is, it does not actually exist with the existence of this axion.
how are different from WIMP?
So they tend to have different types of interactions. So they don't necessarily interact through directly through the weak nuclear force. So they have couplings to gluons. They also can decay into photons, but they have very, very low masses. So like micro EV masses rather than WIMPs, which have like 100 GeV. So that's a large difference. So it's like milli EV to micro EV. They can decay though into photons, but because their mass is really low, and because of other effects, the decay happens very, it's a really, really low rate. You can induce this decay in principle, but it by itself, it's very low rate. So the decaying dark matter isn't the problem. But yeah, so it's, and it also solves different problems if you include it in your beyond the standard model theories. But the idea with this axion is that it makes it so that the CP violation does not exist anywhere in the universe. So it solves this strong CP problem globally. Okay, so if you looked anywhere in the universe, the neutron electric dipole moment would be 0.
Okay, yeah.
The difference with our idea is that we've only measured the neutron electric dipole moment here on Earth. So, you could go ahead and say, like, let's take a look at maybe this is a global thing, right? We measured the neutron electric dipole moment here, and it's the same everywhere. But we can't say that for certain, right? That is an assumption. So what if you go with the other assumption that maybe the neutron electric dipole moment measured here being 0 is a fact of the environment that the neutron's around. Maybe it's some sort of terrestrial thing right? Some terrestrial effect. Um,
Mhm.
and in our case, what we're saying is that we introduce this, we know that dark matter, lots of dark matter exists in our, in our solar system, in our galaxy, etc. And what if it's the fact that there's lots of dark matter around the Earth, around the experiments, and that effect that cancels off the theta term. But if you looked at a place in the galaxy that didn't have a lot of dark matter, maybe you'd see a different value, some non-zero value for the neutron electric dipole moment. And so that's the general idea, is that you can have some sort of effect that depends on the amount of dark matter that you have around, whether or not it actually solves the strong CP problem. And so the way that we do that is by taking a bunch of these dark matter particles. They have to be very low mass, and they're vector bosons, like a photon with mass. And it's their spins that interact in a certain way that the more that their spins can interact, the more that their spins can align, something like magnetism or something like that, the more collective effect that it has that cancels off this neutron electric dipole moment. Okay, when there's not enough of these dark matter particles, their spins can't interact enough and align enough to actually cancel off the neutron electric dipole moment. That's the general idea. The cool thing about this is that we can detect, we can in principle detect a kind of smoking gun signature through stellar spectra. So if you have a neutron electric dipole moment, what that does is that actually changes the physics of, like, say, the hydrogen atom. Okay, so if you have an electric dipole moment, right now, if you're looking at the potential that you put into your Schrodinger equation, it's not just a Coulomb law. It's Coulomb plus an electric dipole moment, right? Some dipole term.
Okay.
And that changes the energy levels that are allowed for hydrogen.
Mm-hmm.
And so that will change the different transitions that you can make. Okay. And so you can in principle distinguish between the different spectra of stars that are near us, that are surrounded by lots of dark matter. And let's say if you looked at dark matter that was very far out in the outskirts of the galaxy, if there's not that much dark matter out there, then in principle, you would get some amount of neutron electric dipole moment. You'd get a reasonably, a slightly different spectrum. And you might be able to distinguish between when the hydrogen atom in the stars has a neutron electric dipole moment and when it doesn't. And if you can do that, then you can map where has a lot of dark matter and where doesn't have a lot of dark matter, right? Because the neutron electric dipole moment existing depends on the amount of dark matter that's surrounding, the neutrons.
And do we have any detection method with which we can verify this?
So yeah, if you do, so currently, I should say currently, no, we don't. The only issue is not that we don't have, a method that we could use. We know how we would do it. It's just that our telescopes aren't quite sensitive enough. So if we used kind of the best telescopes for spectroscopy, right now they're about an order of magnitude off in sensitivity. So like next generation telescopes would definitely be able to do it. It's just that the changes are very slight, so that the emission lines that you would see, the differences, they would be right next to each other, and it would be very difficult to distinguish between the two different emission lines. And so you'd need a really sensitive telescope, but we're not that far off. Like, again, next generation telescope that does spectroscopy would be able to see it. If it were there, it's highly speculative, of course, and it may not exist at all. But, if we don't find that signature when we think we should, that actually tells us very good information, right? That rules out a particular class of dark matter models, or at least one particular idea, right? So null results are very useful as well.
Okay. Like before going further, I have a question. Like we have a question from Mehul Tiwari 6, and he's asking that what kind of sensor? Wait, let us disappear. What kind of sensor could sense that kind of force that is still unknown? So, like he's talking about the forces which are currently we do not count in our standard model.
Yeah, so
So,
that's a really good question, and it's a tough thing to answer. Um, for some of these, all that you need to know is or assume is that the dark matter and standard model, things like dark matter and quarks, interact either via that unknown force. Maybe it is completely unknown. Maybe it's they interact through the Higgs or something like that. But it ultimately doesn't matter what that force is if it can jostle those atoms, right? So you don't necessarily always need to know what the details of the force are, because even if it's unknown to us, if it is how the universe works, then it's going to have an effect, right? Maybe we just don't understand it yet. But we will see something like in our detectors, we might see some signal and we just won't understand what's exactly causing it yet. But then we have to rush and figure out, okay, what's actually happening here. Right. So we
yeah.
would see
Like,
something like,
maybe we have a particle X which is going through us, but it do not interact with any of the forces we have known so far. So there is no way of detecting it, not and no way of knowing that this kind of particle exists. So I think we cannot do anything about it. It's how just universe is.
yeah, and it's possible that the particles do interact. It's been very weak, and we need to create very sensitive experiments that maybe for a lot of these experiments, you don't have to pick exactly how it interacts. It's just going to be you know, the assumption is that it does interact. And so if you have dark matter bumping into these atoms, maybe we don't know the details of what's interacting, what the exchange particle is. But if it bumps into the atoms and we see those atoms kind of jostle around,
Mm.
then then it's possible that we just need to understand what that new thing is, right? We could it could still be something completely new and unexpected. But if we see some signal in our detectors, we may just not understand what that signal means, yet.
Cool. And we have another question from Vivek, our friend. Could you explain the relation of dark matter with cosmic microwave background radiation?
Yeah. So I'll do my best. I'm not an expert on kind of the more detailed cosmology side of things. But I will say that uh, as far as the structure of the CMB goes, dark matter has played a very important role. And if you actually take a look at if you take a look at what's called the power spectrum of um, of the CMB, it turns out that you get a very particular shape, you get a very particular curve, and if you include dark matter into this story, uh, it fits the data so incredibly well. Um, I will, if you don't include it though, it's actually pretty messy and does not work at all. Um, and I will say that there could be some interesting things, um, between the dark matter and it interacting with, um, some of the physics while the CMB was. Actually, no, I don't think that's. I'd have to think about that some more. I don't think that you can really modify the CMB much or like any sort of real dark matter interactions because that's after BBN. And back to Big Bang nucleosynthesis is pretty well confirmed. So I don't think there's much you could mess around with. But it does, as far as like dark matter's gravitational interactions and how it's clumped up to form galaxies and all that kind of stuff, that is imprinted on the CMB. And you can measure the kinds of, you can actually measure the abundance of dark matter using the CMB and all that kind of stuff.
Okay, that's cool. So, like, I would like to go to the next topic here, and it was on the internet everywhere few months ago, and it was regarding the discovery of Anita that was related to parallel universe results. So basically, there was an experiment where they detected tau neutrinos coming from the side of the Earth from where they were not expecting it, and that's why no possible explanation was there to explain this, and that's why people said that maybe either there is parallel universe or there is new physics which we don't know. So what are your views about it?
Um, yeah, so I would tend to lean towards something that's hinting towards beyond the standard model things, some stuff that we just don't understand yet. Things are
Same here.
very things are very complicated, and there are lots of things in this universe that we don't understand currently, right? We know that the standard model is not a complete theory. For one, it doesn't include dark matter, doesn't include gravity, doesn't answer a lot of questions. It doesn't answer the strong CP problem, doesn't answer something called the hierarchy problem, which has to do with the Higgs mass. So there's lots of problems with the standard model that we don't understand. It does predict a lot of things very well, but there are definitely things that you know we need to understand. And it wouldn't be so surprising if these strange signals had some sort of dark matter origin, right? So when astrophysicists are saying that there can't be any sort of astrophysical origin, what they're saying is that there can't be any sort of astrophysical origin accounting for all of the known physics, right? So
Okay.
if there could still be some astrophysical origin, but it could be something like dark matter, it could be some other physics that we don't understand. Maybe it could be something to do with the Earth. Um, there could be some geological process that's screwing things up a bit that we don't truly understand either. Um, I would be hesitant to say that um, parallel. This is evidence for parallel universes and all that kind of stuff. I don't know how much I really buy that, or if that's just kind of a it's something that could, I guess, be there on top of the other. Maybe I shouldn't say more likely things, but in my opinion, would be more convincing. I would be more quick to accepting beyond the standard model stuff before
Yeah,
parallel
it
universe.
kind of was, with which you can get more traffic on your website or more viewers, because when the parallel universe things comes, people tend to watch it more.
Yeah, yeah, absolutely. That's very true. Yeah, it's a very exciting title for a post or something like that.
Okay, we have a question from Mr. Varun Reddy. Can you say anything about the life that was discovered on Venus? Like, I would like to speak on it that it's not confirmed that we have discovered life on Venus. It's just phosphine. Now, the case is that it's mostly emitted by the microbes on Earth. And that's why we are expecting that it might happen, but that's totally that's not only the case. There are many volcanic activities which can also release those gas. So I don't think we should simply jump to the conclusion that there is life on Venus. There might be some other events which we are not very familiar with. Now, coming back to the topic, so here's the current standard model of the universe. And when we talk about the physics beyond standard model, so when we talk about it, what it actually means, it means that we have to add additional particle to our standard model, or it will completely breaks down and we have to create a new system, like which used to happen with the periodic table during early time. We have Mendeleev's table, and then again new kind of table, the new table. So what do you think physics beyond standard model actually means?
I think that it's probably, I mean, it could come in a couple different forms, but I think that uh, the way that we have it set up right now is pretty firm and does agree with tons of um, experimental results. And so the thing is that the structure of it is quite solid, and I think that anything that you do right now is going to be adding on to it. Maybe it's going to be kind of similar to a periodic table where you slide some new ingredients in the middle somewhere. Um, we might have to adjust it, but I think that the structure that is there will just be will be pretty firm, but maybe we'll put some additional structure on top of it, right? So maybe there's some new symmetries of the universe. Maybe there's some other more complicated physics that kind of unifies everything into one more coherent picture. But fundamentally, or as it stands, the structure that we have does seem to be at least partially right, right? So I don't think that it's going to be a complete reworking of it, more of a adding some additional ingredients in and probably making it a little more coherent and cohesive in the future. But I don't think it's going to be as drastic as kind of a complete rewriting of it.
Okay, so we have another question from physicist Islay. I don't think I'm saying the name correct here. So the question is, in the cosmological model of quantum fluctuations, can there be a finite number of bubbles in bracket universe at t is equal to 0?
I can't say one way or the other. I don't see why not, but I'm by no means any sort of expert, and I haven't studied anything like this in detail. So yeah, I think that I should probably just express my ignorance and say that I do not know. I would imagine that you'd prefer finite numbers of things rather than infinite numbers of things, but in principle, you're not. I don't see anything wrong with it. But again, I am by no means an expert and can't really say one way or the other. Sorry.
Yeah, it's very hard to imagine such scenario.
Mm-hmm.
And one of the person here wants to talk you about graviton and its place in the standard model. So I hope you have some time left, right? Or should we end?
I have just a couple of minutes. I do have a meeting at 10 my time.
Okay, so I will simply, jump to the last part of the session. Is there any advice you would like to give to the students who want to go in the field of dark matter physics and want to work in the field of high energy physics? Is there any piece of advice?
Yeah, so I think that one, the kind of standard thing is, really learn the basics very, very well. Learn your quantum mechanics, learn your classical mechanics, pay attention to everything. Also, statistical mechanics, as painful as it can be sometimes, is very important as well. But the thing that I would also say is that, doing things like research can be very important, and it doesn't necessarily need to be in dark matter or particle theory or anything like that, or even particle experiment. There were some of my classmates who had never done particle theory research or particle physics research at all. They had done some other research, and there's a lot of things that you can learn just from doing any type of physics research, right? There's stuff that is very much applicable to all fields. And so if you do that, then you get an idea for what research is like. And I would definitely say that don't necessarily hold out and saying that okay, I need to do particle physics research to say go to a PhD program in particle theory or particle experiment or something like that. All research is very valuable. And so you don't necessarily need to only have done research in that specific area to go to grad school or something like that for it. That's just not the case. In particle theory can be pretty difficult to do as an undergraduate, and there might not be that many opportunities. You can find them, but there might not be that many, and it might be kind of near the end of your time. So
okay,
yeah,
that was very useful. It's even useful for me also. That means that we have to be open for many research field, and we should not just bound ourselves to one thing only.
Yeah, absolutely. Even if your ultimate goal is to do particle theory research, that's not the only thing that will lead you to particle theory, right? Research in general is a good skill to acquire, and so it's going to help you in particle theory research too, because it'll teach you the type, the ways to think and all that kind of stuff.
And I guess we are out of time now. Like it's going to end in 10 seconds. So thank you very much, Jason, for giving your precious time. And I will be looking forward for such more live conversation in future whenever you
Yeah,
get time.